This is the second video that we are talking about the derivative of inverse function. In this second video, now we wanted to find a formula that will help us to evaluate the derivative of the inverse function. In the first video, we talked about the function f and its inverse and what are the properties that these two functions share. For example, if f is continuous, then f inverse is continuous as well. If f is increasing function, then f inverse is increasing as well. And if f is decreasing function, then f inverse is decreasing as well. This is going to be the content of theorem 3.7.4. In this theorem, it says that suppose that f is differentiable functions on an interval I, and f prime of x is not equivalent to 0 for all points x's inside the interval I. Now, if the function f has an inverse function on I, then the inverse function is differentiable at a number x, and the value of the derivative at this point x of the inverse function d over dx of f inverse at x is equivalent to 1 over f prime evaluated at f inverse at the point x. Like any other theorems, you need to split it into two parts. What is the hypothesis of this theorem? And then what is the conclusion of the theorem? Now, the hypothesis of the theorem is given in blue color. That is, your function have to be a differentiable on some interval I, and also the value of the derivative is non-zero for all the points inside that interval I. Also, the other hypothesis is that if your function f has an inverse on this interval, then the conclusion of this theorem says that is your inverse function is going to be a differentiable at a point x, and also the value of this derivative is going to be given by the mentioned formula. But in this formula, notice that in order to evaluate the derivative of inverse function f at the point x, in the expression you need to have what is the value of the inverse function at the point x. But do you really need to have the expression for the f inverse here? Well, actually, we don't. Well, let's see. If we don't have the exact expression for the f inverse, then how are we going to evaluate it at certain points? Well, we're going to use the special property between the function f and its inverse. To make it more clear for you, let us see the next example. In this example, the question says, find d over dx for f inverse at the point 5. If your function f is 1/3 of x cubed plus x minus 7. Without computing f inverse of x explicitly. So he doesn't want the function for f inverse, he just needs you to find the derivative at the inverse function at certain point, which is 5. Well, first of all, we need to know if you're given this function f. Now, since f is a polynomial, it is a continuous function and differentiable on the whole real line. Also, if you compute the derivative of this function, you find that it's going to be x squared plus 1, which is a positive quantity for any real number. Well, it follows from theorem 3.7.3 that f is going to be a one-to-one function and it's going to have an inverse function, so f inverse exists. In addition, this theorem tells you that your inverse function is going to be a differentiable. Now, in all these above statements, the hypothesis of theorem 3.7.4 had been satisfied, so we could use the theorem and its conclusion. The conclusion of that theorem says that is the derivative d over dx of f inverse at the point 5 is equal to 1 over f prime at f inverse at the point 5. To do the calculations for f inverse at the point 5, now you know that if you let's say that y is equal to f of x, then this is equivalent to saying that f inverse at the point y is equal to x if you take f inverse for both sides. Now, if we're choosing the value for simple y to be 5, then what is the corresponding value of x? Well, we don't know what is f inverse, but we know what is f. So use the first sentence. 5 is equal to f of x. Now you know what is f of x is 1/3 x cubed plus x minus 7. Well, if you simplify your equation a little bit, then you are going to get that x cubed plus 3x minus 36 is equal to 0. Well, from previous courses, you know that if you've been given an equation like this one, and you've been asked to find what is the solution of these equations, then one way of using or trying to whisper the solution for rational solution for this equation is that rational zeros theorem. Now, this is going to give you a list of all the possible rational zeros, which is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, and plus or minus 36. Now, by trial and error, try to find which one of these ones is going to work as a zero if this equation have a rational zero. Well, by the trial and error, you will find that the winner is going to be number 3. So this means that 5 is equal to f of 3, which is equivalent, like previously what we did. If we apply the f inverse for both sides of this equation, then this is going to give you f inverse at the point 5 is equal to 3. And this is the value that you've been looking for. Now, going back to the formula that we have in the previous lines, d over dx of f inverse at the point 5 is equal to 1 over f prime and f inverse at the point 5. Now, we know what is f inverse at the point 5. It's equal to 3. So, this is equivalent to 1 over f prime at 3. We know what is the derivative of f because we know what is the function f is. Then, the next line is going to be 1 over 3 squared plus 1, which is just equivalent to 1 over 10. And this is going to be the answer that you are looking for. Sounds easy? Well, if you follow all the steps in this example and you are confident about it, try yourself in the next question. The next question says that let the function f be equivalent to 2x cubed. Find the derivative of f inverse at the point f of 1 and 1. Remember, if you are using any theorem, verify the hypothesis of any theorem that you may use. Good luck!